graduate dean here at Montclair State University. President Cole, Provost Pinkley, honored guests, colleagues, students, ladies and gentlemen, I'm indeed honored to welcome you to the Fall 2009 Margaret and Herman Sokol Science Lecture, titled Gravitation, from Galileo to Einstein and Beyond. Montclair State University inaugurated the Margaret and Herman Sokol Science Lecture Series to bring to our campus world-renowned individuals who have an outstanding record in their own discipline and appeal broadly to other disciplines. Established to promote a deeper appreciation of important issues in the sciences, the series has been funded by a generous gift from alumna and very good friend Margaret McCormack Sokol in memory of her husband and also MSU alumnus Herman, who was instrumental in discovering the antibiotic tetracycline and served as president of Bristol Myers Company. Margaret passed away in June of 2006, but this series continues to honor this outstanding couple's contributions to our university. This lecture also celebrates the year 2009 as declared by the UN, United Nations, as the International Year of Astronomy, honoring the first use of the telescope by Galileo Galilei 400 years ago for astronomical observations. As such, this lecture is also sponsored by the Joseph and Elda Coccia Institute for the Italian Experience in America. Ever since the dawn of humankind's existence on Earth, astronomy, more than any other branch of science, seems to capture the imagination of the average human being, partly in awe of the beauty of the skies, and partly due to the fear and apprehension of the unknown and the uncontrollable, but also as a question often arises of the meaning and effect of the stars in our lives. The skies were studied for thousands of years with the unaided eye by many scholars from ancient China, Babylonia, Assyria, Greece, and the Americas. But it was the genius, the practicality, and originality of Galileo Galilei to use a telescope, developed for more practical purposes to help this eternal investigation of the skies. In Stephen Hawking's words, Galileo, perhaps more than any other single person, was responsible for the birth of modern science. He was a physicist, mathematician, astronomer, and philosopher, and very importantly, one who used experiment to validate hypotheses. In the tradition of another great scientist, mathematician, and astronomer that lived in the great land of Italy, Archimedes of Syracuse, he combined knowledge and discovery to the development of practical tools. Even though the telescope was first developed in the Netherlands a year earlier, upon hearing about its concept, Galileo developed overnight his own version with original magnification of 3 times, not very much, which soon became 33 times. Galileo was an entrepreneur, not just a scientist, and he successfully marketed the telescope that he developed to his contemporaries in Venice as a tool for sea navigation. His own curiosity and thirst for knowledge, however, made him turn it up towards the skies, and for the first time in mankind's history, see the heavenly objects as more than just decorations in the sky. He recognized, for example, that what the rest of us saw as the face, it was actually craters, hills, and valleys on the surface of the moon. He discovered the satellites of Jupiter, the spots on the sun, and the faces of Venus. He saw evidence that the Earth is not as unique as previously believed, and he proved the rotation of the Sun on its axis. This event, aiding the naked eye in this investigation, was groundbreaking, history-changing in the mankind's understanding of the world. In the same way that we may say that later, the humans first photographed the other side of the moon using a Russian satellite, or more gloriously for the American nation, when the first human landed on the moon. The land of Italy has a long history of producing many great scientists, engineers, and entrepreneurs. Too many to adequately mention here. Let me, however, single out one of my favorites, who clearly followed in the footsteps of Archimedes and Galileo, a more recent great, Enrico Fermi, who too was known for his entrepreneurial spirit, tenacity, mathematical and scientific talent, the ability to explain simply complicated concepts, and to pursue practical applications of science, like, for example, the first sustained and controlled nuclear reaction that led to the first nuclear bomb, and the harnessing later of nuclear energy for peaceful means. Before I introduce to you our today's speaker, I would like to briefly introduce Consul Andrea Barbaria from Italy, from the New York office.
Thank you so much. Ladies and gentlemen, I would like to thank the Montclair State University, and particularly President Sokol, and of course the Kocha Institute for inviting me here tonight, and also for deciding to host such an important conference. I also bring the greetings of the Consul General of New York, Francesco Maria Talò. This year we celebrate an important anniversary. More than 400 years ago, the Italian astronomer and scientist Galileo Galilei was developing a newer and more advanced version of the telescope and was observing for the first time the lunar surface together with the other celestial bodies of the solar system. Galileo Galilei was an extraordinary scientist, as Professor Eugenio Coccia, director of the Laboratori Nazionali del Gran Sasso, will soon tell us, but he was also an important literary figure. He somehow developed the first example of Italian literary prose. For all these reasons, we can say that Galileo Galilei, a mathematician, astronomer, philosopher, and writer, totally represented the Renaissance ideal of a wise man, capable of adapting and expressing himself in different aspects of human knowledge, and willing, like Cristoforo Colombo in his own field, to extend as much as possible the limits of the human knowledge. Thank you, and enjoy this Sokol of Science lecture. Thank you very much.
And now to the main event. Today's speaker, Dr. Eugenio Coccia, is another distinguished son of Italy, a physicist who has dedicated much of his life to the understanding of the nature of the most common in our daily experience, phenomenon and force of gravitation, and also the origin of matter. Gravitation has always intrigued people and was studied by Galileo and many great other scientists that followed, especially Isaac Newton and Albert Einstein. Professor Eugenio Coccia has graduated in physics in 1980 from the University of Rome, La Sapienza. And since 2003, he has been the director of the Gran Sasso Laboratory of the Italian Institute for Nuclear Physics, the world's largest underground laboratory for astroparticle physics. He is also a full professor of astrophysics at the University of Rome, Tor Vergata, and leader of the cryogenic Gravitational Wave Detectors Explorer at CERN, a major European research institution in Geneva, Switzerland, and Nautilus at the Italian Institute of Nuclear Physics at Frascati Laboratory, which is outside Rome in Italy. He is the former chairman of the Scientific National Committee for Astroparticle and Neutrino Physics at the INFN, a position he left after becoming the director of the Gran Sasso Laboratory. Dr. Coccia has also served as the president of the Italian Society of General Relativity and Gravitational Physics from 2000 to 2004. I might note that even though Eugenio Coccia is not related to our friend Joseph Coccia, he has not been a stranger to our geographical area, as he maintains a close collaboration with scientists to our south at Princeton University. I'm very happy to present to you Professor Eugenio Coccia.
Thank you very much. Of course, I thank for this invitation President Cole and also the Coccia Institute. I'm happy to be here to tell you today about gravitation from Galileo to Einstein and beyond. It is a journey through the universe, which I hope we will do together tonight. Let's start with this picture. This is a picture taken by the Hubble telescope. It is a deep picture of the universe. You see every point here, every of this luminous region is a galaxy. Galaxies are like islands in the universe. Island made of collections of stars. This is one of the galaxies which is near to us, the Andromeda galaxy, in which there are billions of stars. Billions of stars in a galaxy and billions of galaxies in the universe. So we are really in front of an immense cosmos. This is another picture which I like. Is perhaps the most beautiful of the planet of the solar system is Saturn. In every picture I show, there is a force which actually acts like a sculpture. It forms structures, galaxies, planets, and stars. Actually, the situation, as human understand this once upon a time, was that the Earth was at the center of the cosmos. And all around there were circles, spherical circles, with the moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and so on. So this geocentric model was a model which actually holds for many, many years. It was quite natural. We are here, we are steady, we see the sun that moves, we see the moon that moves, everything moves, but we stay here steady. So it was quite a natural way of thinking, the one in which the Earth was at the center of the universe. Also psychologically, it is natural to think we are at the center of the cosmos. Well, actually, this man, Copernicus, in Polish, Copernik, which means the man of the copper. Actually, his father was a copper merchant. He wrote this book after several journeys in Italy. He studied in Italian cities like Bologna, Padova, and Ferrara. He graduated in law, actually, in Ferrara. But what he wrote just at the end of his life, this book was printed the very last day of his life. In this book there was another model, a model which was previously, once upon a time, by some Greeks, also thought as possible, in which the Sun was at the center and all the other planets, including the Earth, moving around. Now, this was published like a mathematical model. It was simpler to calculate the movement of the planets, to predict the movement of the planets in a model, in a reference frame, let's say, in which the Sun was at the center. As such, as a mathematical model, this was disturbing nobody, even not the Roman Catholic Church. It was impossible to ignore, however, what this man demonstrated experimentally by observations. This man is Galileo Galilei. Here is 40, and this is the instrument of the revolution, is a telescope. Actually, he did not invent the telescope. The telescope was invented in Holland, but was invented as a practical instrument to look to the ships, to look to the terrestrial things in a magnified way. He was the first one to point the telescope to the sky. Actually, he got funding from the Doge in Padova, saying that this instrument, which he improved respect to the previous version in Holland, was useful for many purposes, including navigation and understanding when the enemy was coming toward us in the sea. Actually, of course, you can see that of course he obtained funding also because of this, let's say, terrestrial uses. But what is important is that he actually pointed this telescope for the first time to the sky. This is the original telescope of Galileo. This is in L'Aquila, where there was the G8 meeting in July, and there was an exhibit of the best Italian things, which President Obama and all the head of states have seen this exhibition, and this was exhibited the real telescope of Galileo. This is a picture I made because I had the privilege to visit this exhibit also. And this is one book of Galileo with the drawings of the moon. So he was showing that the light of the moon was not its own light, was the light of the sun reflected by the moon. He saw that the moon has valley and mountain like the earth. This fact that the moon was possibly made like the earth was revolutionary at the time. And even more revolutionary was another discovery. This is the book of the original book of Galileo with his notes. Let's see part of it. This is in Italian. It's in ancient Italian, actually. I will try to translate to you. This is the very handwritten piece of paper by Galileo. He says, AD 7 di gennaio 1610, 7 of January 1610, Jupiter, Giove in Italian, Jupiter was seen with the cannon, called cannone. The cannon was not the cannon, was the name of the telescope at the time, because of this form, you see. Cannon telescope was a later word, of course, and was seen with the cannon, and 3 stars, fixed stars, in this way. This is the drawing, this is Jupiter, and this is 1, 2, 3 stars. No one of these stars was seen without the cannon. Without the telescope, was not possible. The naked eye, you didn't realize that Jupiter had these 3 luminous points. So this is already a discovery. What are these? Are small stars moving with the rest of the fixed stars of the sky? No, because in fact after, he says, in the day 8, so it was the day 7 of January, this is day 8, they appear in this way. This is Jupiter, and the 3 stars, 1, 2, 3, all 3 on one side. This was very strange. And then, after some note, he said that the motion was direct and not inverse, like the calculators says. The calculators are the men made in calculus of the movement of the stars and the planets. So the motion of the stars was in one direction, but three stars near Jupiter seemed to move in the opposite direction. In the day 9, it was cloudy. No observations. And in the day 10, it was possible to see like that. 1, 2, and the third was just in an eclipse in front of Jupiter. And he says that the stars was in front of the other. He was observing as small solar system in practice, another small solar system. This system of objects were moving around Jupiter, Galileo soon understood. This was revolutionary because it was even worse than the sun being the center. This was another center of another system in its own. Now, today, we know, because of many observations from the Earth and from the sky, from the space, that there were the Jupiter moon, the 4 bigger Jupiter moons, called the Medici, because of the Medici family sponsoring Galileo in his research. We know very well the surface of this object. They are fascinating object, and this was a demonstration, practical demonstration, that what Copernicus said maybe was not only a mathematical model, maybe really the sun was the center, and every gravitating object may be the center, every object, the mass, may be the center of something else revolving around. So, in one of his best book, he say, philosophy is the name at that time of natural science, and so also physics. Philosophy is written in this grand book, The Universe, which stands continually open to our gates. But the book cannot be understood unless one first learns to comprehend the language and read the characters in which it is written. It is written in the language of mathematics, and its characters are triangles, circles, and other geometric figures, without which it is humanly impossible to understand a single word of it. Without this, one is wandering in a dark labyrinth. So, the universe is written in the language of mathematics. This is a very deep statement. This statement, and mainly the observations of Galileo, what really had as a consequence is that marked, together with the Copernican revolution, the observation of Galileo supporting the Copernican model marked the affirmation of the scientific method and of modern science. The sun is at the center of our local universe, and all the planets are around it. So we have the statement of Einstein and Hawking, and the one of Einstein's is that pure logical thinking cannot yield us any knowledge of the empirical world. All knowledge of reality starts from experience and ends in it. Propositions arrived at purely logical means are completely empty as regards reality. Because Galileo saw this, and particularly because he drummed it into the scientific world, he is the father of modern physics, indeed, of modern science altogether. This is also recognized by Stephen Hawking. Galileo, perhaps more than any other single person, was responsible for the birth of modern science. You have not to read on the book which is the truth, you have to experience the truth, you have to prove that this is true by observations. Now, this fact that the language of the cosmos is the mathematical language is also another statement, apart from the fact that you need experience to prove, as a proof of your statement, but also this fact of mathematics is very interesting because the fact that nature has secret harmonies that we can understand. In fact, if the language is mathematical, we can understand it. We know we can understand it. These harmonies are expressed through numbers. Why I say harmonies? Well, because expressing in numbers the things may be harmonic, equations may be beautiful. This point of view, which we will see in the rest of the talk, is very interesting because it came from the ancient Greek and from Pythagoras in particular. In fact, Pythagoras studying the consonances, the sounds that are pleasant, the sounds which are nice. He discovered soon that they may be produced by strings, for instance, which length stays as ratios of integers. The length stays as ratio of integers. So if a string has a length 1, then a length 1 over 2 is called the octave. The 2 over 3 is the fifth. The 3 over 4 is the fourth, and so on. And then all together they give a pleasant sound. If they are not in these ratios, the sound is not harmonic. You feel something not pleasant at all. So the statement of Pythagoras, which can be taken as a guideline even for modern theoretical physics, is that if musical harmony can be expressed with numbers, the same could happen for the entire cosmos. Actually, there are many examples one can make of this. One is the Kepler's 3 laws of planetary motion. So the motion is not chaotic. The motion follows some rule. And there are mathematical rules, can be expressed by words in this way. I think many of you remember these 3 laws. The orbit of every planet around the Sun is an ellipse, with the Sun at one of the focus. And the line joining a planet with the Sun sweeps out equal areas during equal interval of time. And the square of the orbital period of a planet is directly proportional to the cube of the semi-major axis of its orbit. So this Kepler law, mathematically expressed, found the full explication in a wonderful equation by Newton almost a century later. It is possible to demonstrate that from the Newton law, this is the gravitational constant, this is the mass of the first body, the mass of the second body, the distance between the centers of the body, and this is the force of gravitation which attracts the two masses. It's a very simple equation, and through these equations we can derive the Kepler's law and the motion of all the planets. In particular, the idea of Newton was that the gravitational interaction was a universal force. You see, at that time, there were two separate worlds. The terrestrial phenomena, things are falling on Earth, we are tied on the floor, and celestial phenomena, the heaven, which have possibly different laws. Actually, what Newton taught is that, well, you know that there is an anecdote that an apple fallen on the head of Newton, and then he saw, oh, gravity. But not like that. Actually, what probably happened is that he saw an apple actually falling on the ground from a tree, and he started thinking, well, the apple was not near the Earth, what at a certain level, maybe 4 meters. So the gravitational force extends his action up to 4 meters. Maybe the gravitational force of the Earth extends its action even more, and there was the moon. Is the moon falling on the Earth? What Newton calculated was the gravitational attraction that the Earth has on the moon, and found that the movement of the moon was exactly the one which was necessary to be the Earth, the source of the gravitational force. Let's take a look with a simple drawing to this Newtonian synthesis. Let's throw a stone from the top of a mountain. The stone falls on the Earth, of course. Then let's throw the stone with a larger force, bigger force. Of course, it falls a little bit more far. Then let's throw the stone even with more speed, and then it continually falls. But since the Earth has a limited extension, this stone is revolving around the Earth. It starts orbiting around the Earth. Actually, it's free falling on the Earth. So the movement of the moon around the Earth is the one of a big piece of stone which is trying to fall on the Earth continuously. It's tied to the Earth, but it's free falling in the Earth. It's not falling like that, bang, because it has a transversal motion, so it do like that. So, the same gravitational force which holds on the Earth, it holds also in the sky. This is the Newtonian synthesis. And this explains why all the planets have their orbits around the Sun. So, if the ancient scenario was that you needed the space, time, Earth phenomena, heaven phenomena. In the Newtonian scenario, you need only space, time, and gravity force, and you can explain everything with that. This is beautiful until this man arrived. This is Albert Einstein. Look that this is what is called the person of the century here in this cover. Not the physicist of the century, not the scientist of the century, the person of the century. So let us explain in 1 minute general relativity, which is the present gravitational theory. This is a challenge. So because the description of Newton is so beautiful, what is needed more? Why these Einsteins invented something more? Well, the reasoning of Einstein was the following. Or let's say we can tell his discovery this way. Suppose there is a flat world, flat land, and two men living in this flat world. They think their world is completely flat. Okay, so they will perform an experiment, which is the following. they start in a line going precisely forward in a direction forming, direction perpendicularly to the line joining them, okay? They start one near the other in the same direction with the same speed. So they want to demonstrate that if they measure their distance after a while, the distance is always the same. Because if they are in a flat world, they go straight in a direction perpendicular to the line joining the other, so with the same speed, so their distance cannot change. But the experiment says that they are going more near. So they think, okay, something wrong. Let's repeat the experiment. They repeat the experiment again and again. It's always like that. They get near and near as soon as they go in this direction. So they can conclude, well, there is a force attracting each other. Or they can introduce another explication, which is that their world is not flat. Maybe they are in a curved space. So in this case, there is no need to introduce an additional force to explain the phenomena. Because, of course, if they start from the equator, for instance, and they go in the direction of the pole, then, of course, they go near and near because it's the geometry which brings them near and near. It's not a force, not an external force. It's just the geometry. They are free to move without any force, but the geometry is such that they observe the distance between them diminishing. So, what Einstein thought was that in our world, which is three spatial dimensions, not two, but we don't need to introduce the gravity force if we think to live in a curved space-time. The sun, for instance, with its presence, causes a curvature in the space, and a planet is revolving around, is orbiting around, not because of the gravity force, but because he is obliged to follow a curved orbit around the sun. And it works. I mean, the Newton's view, the Newton view and Einstein view can be seen as alternative, but working well. Actually, there are many experiments showing that the Einstein view is the right one, is correct. And we see this in many examples. In particular, it is possible to see that from the Earth we see a star in a different position respect to the one it is really, because the real star light it curves around the sun, and so from the Earth we see the star here while the star is there. So this deflection of the light can be explained fully in the Einstein general relativity theory. So in the view of Einstein, the synthesis is extreme. The Einstein scenario is space plus time plus Earth phenomena plus even phenomena. The Newton scenario is simpler, space, time plus gravity force. The Einstein scenario is even simpler. It's curved space-time. Matter deforms space-time, and then every object moves free in this curved space-time. This is the Einstein revolution about gravity. Through Einstein law, we can explain all the phenomena in the universe, and we can explain also why star forms. This is also explained well by Newtonian mechanics, but let us fix what piece of art gravity is able to perform with the star. This picture is the sun. The sun is bright, it's wonderful. What is the mechanism? Which is the motor of the sun? Well, we know that the motor of the sun is the thermonuclear fusion at the center. How a star works? Actually, gravity, after the Big Bang, there was a lot of hydrogen everywhere. This hydrogen condenses because of gravity. It's compressed because of gravity. As the compression goes on, the temperature at the center of this cloud is higher and higher. And billion of degrees inside the star. The temperature is so high, temperature means the kinetic energy, the velocity of the protons, which are the nucleus of hydrogen, is so high that to win the electrostatic repulsion of the protons, which are same electric charge, so they tend to repel, but with such a speed that they go so near to trigger the nuclear force, which works only at very small distances. You must oblige the protons to go nearly touching for triggering this nuclear force, which is attracting and then release energy as the fusion happens. So this has two results. One is to form from hydrogen the nucleus of the other elements. The nucleosynthesis is called this phenomenon. So from hydrogen to helium, to beryllium, to carbon, nitrogen, oxygen. This is happening, releasing a lot of energy. And this energy is the energy of the sun, is the light of the sun, the particles coming out from the sun. So this mechanism of the nuclear fusion occurs right in the center of the sun, and it equilibrates the gravitational force. Gravitation tends to compress the star. At a certain moment, the temperature is so high at the center, nuclear fusion starts, and radiation starts coming out. This radiation is opposite to the gravity. The radiation which comes out tends to expand the star. So you have gravity which compresses, nuclear fusion causing radiation which tends to expand, and you have an equilibrium between gravity and radiation which comes out. In this equilibrium, the stars lives for billions of years. The sun is in the middle of its life. And in this picture, you see clearly the radiation which goes out from the sun and which make the resistance to the gravity which tends to compress. So this is a miraculous equilibrium lasting, we are lucky, lasting billions of years. And you see the dimension of the sun respect to the planets in our solar system. This is the Earth. This is Jupiter, which is considered a giant. This is the sun. Incredible. The sun is really our giant. But it's not a giant in absolute. In fact, this is the sun respect to Sirius, to Pollux, to Arcturus. Other stars we can see in the sky, even with naked eye. So, is Arcturus the real giant? Well, no, because actually Arcturus is this one. What respect to Betelgeuse or to Antares? Yes, they're monsters in the sky, these stars. Incredible. So our sun is small, a poor child. And this is a picture which should touch us. We should be moved by this picture. This picture is a representation of clouds, of dust, of hydrogen condensing. This is really like a little baby which is not yet born. And from this cloud, one or several stars will form. This is a fantastic, real picture of what is happening in the universe. Stars are continually forming, and and evolving. This is the end of a star. What happens? That I explained the gravity is responsible for triggering, for starting the nuclear fusion. And the nuclear fusion is responsible for forming all the elements, from the helium up to the iron. At the iron stops the nucleosynthesis. After the iron, you need too much energy. So, at a certain moment, a lot of iron is formed, hydrogen is ended, the fuel is ended, and there is no more this radiation which makes the resistance to the gravity, and the gravity wins. How the gravity wins? Well, for our sun, which is small, the gravity will win slowly, and the sun will reduce in dimension and will end its life like a dead star, dead piece of iron. For bigger stars of several solar masses, the end is catastrophic, because like if you turn off a switch, the fuel end and the gravity is so strong that in a fraction of a second, the star collapses, there is a bounce and explode all around. The ancients saw this new, it's very bright when it explodes. The ancients, they saw this new point of light in the sky. They call it the new stars, novae. Very big supernovae. So the supernova is the end of the big star. And it's very important, its end, because all the elements formed inside the star is at that moment that they go all around the universe. Carbon, nitrogen, oxygen, elements which are fundamental for life are spread around by the explosions of the star. We are made of pieces fabricated, formed in some stars. We are literally star dust. Literally, we are star dust. And I said iron was the end. After the iron, there is no way of forming other elements. But you know there are elements which are more
Heavy. Damn.
more heavy. Excuse me, I don't know why. More heavy than iron, like gold, uranium. When the gold is formed, many of you, I'm sure you have a piece of gold with you. The gold is formed in the moment of the bounce. At that moment, the compression is so strong that from the iron, gold is formed, uranium is formed. It's like an alchemist, the explosion, you see? The star is an alchemist. They really transform one element in another. So all the gold you have is the proof, the experimental proof, that the star ends in a catastrophic way. This is the rest of a supernova, which ancient Chinese astronomers saw in the year 1054. And this is some cloud made of some elements spread around. At the moment of the bounce, something even spectacular may happen. Black holes can be formed. Black holes are really still nowadays are a mystery. What is the concept of a black hole? Can be explained very simply. Don't be impressed by this equation, but you have to know that to escape from the Earth with the satellite, with something, you have to reach a certain speed, escape velocity. For instance, from the Earth, you have to reach 11.2 kilometers per second, and you leave the Earth. So everything we launch on the Moon, on Jupiter, on an orbit, they have they need to be launched at a speed of 11.2 kilometers per second. If you live in a heavier planet, this speed is larger. So the escape velocity depends on the mass, and on the ratio of the mass on the radius of the planet, let's say. So what about a mass so big or so dense? This escape velocity can reach the speed of light, the maximum speed possible in nature. So if you have an object so dense that the escape velocity is larger than the speed of light, then such a body cannot emit or reflect light, and it will appear completely dark. You have a black hole. And at the end of the explosion of a star, of the implosion of the star before the bounce of the explosion, you can have matter so dense to form such an object. Such objects, we think, exist. They can exist at the center of every galaxy. They can form quasars, a very important object in the sky. And following general relativity, at the center of a black hole, matter is crushed to infinite density. The gravity becomes infinitely strong. A space-time has infinite curvature. This means that a black hole mass becomes entirely compressed into a region which is called the singularity, gravitational singularity. Around the singularity is a point inside. This is the event horizon, which is the surrounding surface of a singularity, and which marks the point of no return. You can go near to a black hole, but if you pass the event horizon, you cannot come back. And actually, the gravity force is so strong that when you fall in a black hole, you are spaghettified. This is a new term. You can become like a spaghetti, because the gravity is so strong, so your feet are subject to a gravity force much, much larger than your head, and in this direction the gravity tends to compress. So this is the result. Black holes are observable not directly, but because of the electromagnetic radiation emitted by things falling in the black hole. Like, for instance, at the center of every galaxy, there is this bright zone because matter is continually falling in a black hole. This is a real object in the sky. It is surely a big black hole inside. So, what is a black hole? Someone thinks it's the biggest possible elementary particle because it is characterized only by mass, by spin, and by electric charge. No other feature. It's like an elementary particle, which also has these three features. Or it can be an energy source. This is for sure, because if you find the way to use the strong gravitational field of a black hole, you can get energy. Or the access to another universe. Why we say the access to another universe? This is because of the infinite curvature. Where do you go if you arrive inside a black hole? Maybe this is a connection with another point in the universe. Or maybe it is a connection to another universe. Is there only a universe or not? Another way, we say that nothing can escape from a black hole except the radiation of the matter, which is still outside the event horizon, but the black hole can vibrate also when masses fall in it. And so this vibration is space-time vibration. Space-time vibration are called gravitational waves, and gravitational waves can be detected, and so it's like listening to the universe. It's like knowing what is invisible to our eyes and to our electromagnetic instrument. I will skip this part because just saying that there are detectors basing on various principles. This is the detector, my detector in Frascati, and this is a big detector in Pisa, in Cascina, and there are two big detectors. This is the biggest one in the US, LIGO. One is in Louisiana, the other in the Washington State. These detectors are Michelson interferometers. When the gravitational waves arise, deforms the length of the two arms, and it is possible to detect a variation of the light which interferes in the two arms. I skip this because, well, this is another project, a future project, to put a big interferometer in the sky to measure with a beam of light if the distances between spacecraft changes. It should change when a gravitational wave passes. Let's go to the final part of the talk. So this is the Big Bang, and this is the time. After the Big Bang, there were a lot of elementary particles, then atoms formed when the universe cooled down, and then other macroscopic structure formed. Gravity is fundamental to explain how the universe is formed. Why only gravity, I say, is important? Well, in defining the macroscopic nature of the universe, gravity is important because here there are four fundamental interactions. Gravity is the weakest interaction with respect to the nuclear strong interaction, to electromagnetic interaction, to the weak interaction responsible for radioactive decay. As you see, the nuclear interaction, like the strong and the weak, are very short in space. They act only on distances very, very small. So they do not act after a few of this fraction of a meter. The only two infinite long-range interaction is the electromagnetic and the gravitational. But the electromagnetic has two charges, plus and minus. They tend to be neutral. Atoms are neutral. So they do not form the structure of the universe. Only gravitation, which has only one type of charge, is only attractive, they accumulate. Well, one way to explain this is string theory. String theory is really fascinating. Still is a theory. It's not yet proved, but it's very elegant. It's very harmonic, let's say. It says that the elementary particle, the quarks, which are composed of protons, the electron, which goes around every atom, they are not point, they are extended. The fact that an object like an electron, which has a mass and has a charge, should be a point is a nonsense in quantum mechanics. It cannot be a point. It should be something extended. There will be always some uncertainty which must be connected to the existence of any physical object. So a point is not fair. It could be a string. What is the advantage of being a string? First of all, it's an extended object. It's not more a point. It's extended. Second, a string vibrates. We know that. It's not necessary to be a string, a quantum mechanical physicist to know that strings vibrates. So, the idea is that every elementary particle is a string which is vibrating on a different note, a different musical note, a different normal modes of vibration. And so, like the Pythagorean consonances, we can have elementary particles which are consonances. So a certain vibration is an electron. Another vibration, another note, is a quark. Another vibration in this theory is the graviton. There should be a vibration, is foreseen by the theory, which is the feature of the graviton. It's very important because this is the only theory which is able to predict the existence of the graviton. The other theories, the standard model of elementary particle physics, ignore the gravity. It's too difficult to include gravity. In this theory, it is natural that gravity is included. So this is why it is so elegant. It is so elegant to consider every elementary particle a musical note, of course. So in this theory, it is necessary that there are extra dimensions. Apart the three space dimensions we know, in this theory there are extra dimensions, which are why we did not discover yet this extra dimension, because they are very, very small. You have to go to very small space distance to understand, to go in this extra dimension. An example of extra dimension. If you see a wire, it seems a one-dimensional object. But if you see a wire very near, you see that it is a cylinder, actually. So you know there is an extra dimension. It's not only the dimension of the line, there is also another dimension. So there are dimensions enrolled in space-time. But to understand it, then you should go to very high energy, because this means probing very small distances. And so, following this theory, gravity could be so weak in our fourth dimension, space, 3 space plus 1 time, is so weak because it leaks in the other extra dimension. While the other interaction, they are mainly here. Gravity is here residually. Is mainly in the other hidden dimension. It may seem a tale, but it's like that physicists moves today. In fact, there is a search for extra dimension in the accelerator at Geneva, LHC. How is it possible to find an extra dimension? Well, the sign that they want to see is the following. There is a high energy interaction. High energy means going to see very small distances. So in this collision, it may well be that not all the energy remains here with us in our space. It may well be that this such a high energy is so high that it can open the way for the extra dimensions. And then in this case, in the collision between two particles, there are many other particles which came out, always when there is a collision in these accelerators, but not all the energy remains there. There are particles which disappear, simply disappear. Where they go? In the extra dimensions. So the search at LHC is the search for a missing energy out of the collision. So, the last statement which I made is that the physical laws appear finally tuned to make life possible. This is something which is surprising maybe for someone, but it's true. In fact, even from the gravity side, this is very well demonstrable looking to the constant of gravity. If the constant of gravity were a little bit smaller or a little bit bigger, we would not exist. Too small, then the stars doesn't form, the fusion doesn't happen. Too big, the star burns too quickly to behave, to have a planetary system, and to wait time for the setting up of the life. So together with the other question of there is only one universe or not, this is an interesting because in our universe it's like that, and we see this. But maybe there are infinite universes. In each one, physical laws are different. We live in the only one which is making possible life. So the gravitational journey from the apple falling to ground up to the life and to the access at the dimensions and other universes. So gravity is the force known since more time, I think. First force experienced by man. Still is mysterious. Is maybe a door, an access to extra dimensions and to other universes. Only experiments will tell us which is the truth. This is the lesson of Galileo. And the end is this statement for Albert Einstein. Everything is determined by forces over which we have no control. They're determined for the insect as well for the star. Human beings, vegetables, or cosmic dust, we all dance to a mysterious tune intoned in the distance by an invisible piper. Thank you for your attention.
Thank you, Professor Co-Chair, for a very intriguing last question. Sometimes we feel like being in another universe to go to. Professor Co-Chair offered to answer some of the questions that may come from the audience.
I have a question.
Yes.
My name is Edith George. I am in Professor Mark Topping's Planet Earth class. The equipment in Geneva that's used to find the missing particles of gravity, I've overheard a public concern is that if sufficient particles of gravity are found, there's a possibility that a black hole could be created. What do you think about that?
Of course, this is an interesting question. Thank you. And this concern of us, I mean, because if a black hole is formed, the hypothesis was that it starts growing, sucking the accelerator, Geneva, Switzerland. If it stops in Switzerland, that's always the case. But then it starts in Italy, and that's absolutely unacceptable. However, this is not true for two reasons. One is theoretical and the other is experimental. So the experimental one, which is I think the most important, as Galileo teaches us, is the fact that energy like the one in the LHC are experienced every day due to the cosmic rays arriving in the atmosphere. Cosmic rays are protons generated by the explosion of the stars. They reach such a high energy, much larger than the one of LHC. Every day, the atmosphere is bombarded by such protons, and so this possibility of forming black holes is neglected by the experience.
Okay.
The theoretical explanation is that a black hole, well, I cannot say everything about black hole in 45 minutes, of course, but the black holes evaporates. Small black holes evaporates faster. This is a Hawking radiation. And this radiation having an explanation quite, well, I don't say simple because nothing is really simple in this case. However, space-time is continuously generating and annihilating particles. Even the space-time, which seems completely empty, is continuously generating and annihilating particles. When it happens near the surface of the event horizon, one of the particles go inside and the other go outside. And so, looking the black hole, this radiation comes from the black hole and causes a loss of energy and of mass of the black holes. This phenomena is faster as the black hole is smaller. So if a small black hole is formed, it evaporates immediately. This is the theoretical explanation. I find more convincing the experimental one, that in the atmosphere every day there are collisions at energy much higher than in LHC and nothing happens.
Thank you.
Other question? Yes.
I think that the bomb technology is now at the same level of fission and fusion kind of bombs. But we have no secret funding. To my knowledge, there are no research in this field.
Yes.
You mentioned gravity and attractive forces, but how does that relate to dark or negative energy or repulsive forces that we hear so much about when the universe is expanding? How does that relate to gravitational attraction, the modern theories of gravitational?
Well, first of all, the negative energy of the gravitational field is very important because actually sometimes the Big Bang appears to us impossible because it contradicts the conservation of energy. Before the Big Bang, nothing. After Big Bang, everything. So it is this appears like as a contradiction, but it's not, because it is a positive energy after the Big Bang, which is all the matter, but it is equilibrated completely by the negative energy of the gravitational field. So energy is conserved. About the dark energy and dark matter, which are two mysteries actually still in present research, dark matter is simply matter made of particles we have not discovered, but the gravitational force is the same. So it's not the gravity force that we have to modify, just we have to understand which is this new particle, which is not electric charge, we have not strong electromagnetic interactions, and so it's very difficult to detect, but which forms 90% of the mass of our galaxy. So this is a mystery, but we understand it. Dark energy is still a full mystery, actually. It's like if there was a hidden energy so dark energy in the universe, which expand the universe faster than was predicted. And about that, I tell you that we are moving really in the dark. There are hypotheses, but we don't have yet an explanation for that.
I believe part of the question was also about repulsive gravitational forces.
Well, we have no experimental test of repulsive gravitational effect. Of course, there are theories which may include a repulsion, which is like a cosmological constant in the equation of general relativity, but I think there are no experimental tests on that.
Any other questions? In the back.
Does antimatter exist in the natural world and in the lab world, or purely theoretical?
Yeah, antimatter is something familiar now. The antimatter is formed every day in the accelerators. It's formed every day by the nature. Cosmic rays, which I said to you, protons hitting the atmosphere, they have collisions with the molecules, with the atoms of the atmosphere, and from these collisions, new matter is created, like in an accelerator. And antimatter is created. So we have every day anti-electrons, positron, anti-pion. We have antimatter is something which is not mysterious at all. The gravitational effect of antimatter is exactly the same of the matter. In fact, I say often in these discussions, we know that the moon is made of matter and not of antimatter, just because we send probes, we send a man there, no annihilation, so the moon is made of matter. We know that the universe is made of matter because we see galaxies colliding, and what happens, we see, is the meeting of the same type of matter. Because matter and antimatter, when they meet, there is an annihilation and energy comes out. So the real mystery about antimatter is why the universe is made only of matter, except this occasional generation of antimatter here and there in the energy process. This mystery is this because in every elementary act in which energy forms matter, following the celebrated equation of Einstein, E equal mc squared, this happens every day in the atmosphere, in the accelerators. When matter is created by energy, always, the situation is symmetric. Matter and antimatter are generated in the same amount, but the antimatter fills all around the matter and annihilates immediately and disappears. But all the physical laws are symmetrical with respect to matter and antimatter. So what happened in the Big Bang? Big Bang is considered the moment in which a lot of energy generated matter. It must have generated equal amount of antimatter. So the mystery is, where is the antimatter? And this is a mystery which actually is a subject of active research. A possible explanation, the favorite explanation, is that it has to do with a particular particle named neutrino. Neutrino may be matter and antimatter at the same time. This particle is the antiparticle of itself. So if this is true, this is an hypothesis which is tested nowadays in all the underground laboratories. If this is true, then what happened at the beginning of the time is that matter and antimatter were created in the same amount and they annihilated. But because of a fluctuation, because of the neutrino, it's like two teams playing, but there is one player which plays with both teams. Sometimes with one, sometimes with the other. So a fluctuation is possible, and it gives momentaneously, just for a moment, it makes one of the two teams winning. So all the antimatter annihilated with the matter, which was just a little bit more in that moment. So this residual matter is the one which forms the cosmos today. This is the favorite picture today. Seems incredible.
Of course, people talk about the existence of anti-cosmoses, called worlds that are antimatter.
Well, it is possible that exists some piece. The other explanation is that antimatter is very far and is out of our observation. So there is another universe made of antimatter somewhere else. But this seems very strange. However, if there is a universe made of antimatter, it's at the same dignity of the matter. So it forms atoms, it may form life. Of course, we hope not to encounter an alien made of antimatter, because
Kiss of death. There was another question, I think. Yes?
You said that as we probe these very small distances, we should see a disappearance of particles. Does that suggest a violation of the conservation of mass and energy, or is it sort of like a quantum fluctuation that we see?
well, no, the question is that, no, there is no problem of conservation of energy. The question is that if you want to probe something which is very small, we have to use a radiation which wavelength is smaller than the object we want to observe. This is true even with the microscope. With the optical microscope, with our eyes, we can distinguish objects very small, but not so small like bacteria, for instance. Not so small like a molecule. Why? Because this object is too small to be distinguished with the radiation which are very long wavelength. So we need to resolve the particular of an object, we need a radiation which wavelength much shorter. I can see you because the light, the radiation, has a wavelength much smaller than your face, than your body. So I can distinguish all the particular. But if I use radio waves, for instance, I cannot distinguish nothing here. So to probe very small dimension, I need a radiation of very small wavelength. Very small wavelength means high energy for radiation. So the highest is the impact accelerators are fantastic microscopes, which allows to distinguish quarks, neutrinos, to distinguish very small objects. So to penetrate in the extra dimensions, I need a radiation with the wavelength much shorter than the one used nowadays. So LHC, with this high energy, go to try to resolve, to distinguish such small distances and to penetrate in the extra dimensions. So I'm not sure to have to understand you. I mean, just I don't hear very well from here. So
the Big Bang was the size of a pinhead. Stephen Hawking was claiming it was a black hole that condensed upon itself and then exploded outward. Are there other black holes capable of exploding outwards, creating other universes behind us?
If a black hole is formed, it cannot explode anymore. Nothing can escape from the black hole once formed. So the universe actually, with the Big Bang, which is more the theory which now is has more credit, it generated space, time, all the interaction, including gravitation, matter, and this is expanding. At that moment, it may be there were small black holes. Most of them should have been evaporated up to now. The other black hole, apart this primordial black hole, but all the other are formed by collapse of stars or by a black hole eating, feeded by other mass, and so increasing its volume. This is the black hole phenomenology. So once a black hole is formed, it cannot explode anymore. Can only eat more matter. Actually, about black hole, let me say that if the sun were substituted by a black hole of equal mass of the sun, the motion of the planets would be the same. I mean, the gravitational effect is the same. So it's not eating, it's just attracting. Of course, big black holes have a force of attraction which is enormous, and also a density which is not so big. In fact, while the density of stellar mass black holes is incredibly high, the density of the supermassive black holes is the density of the water. A big black hole at the center of our galaxy may have the density of the water. In such a big, gigantic black hole, you can enter, you can pass the event horizon, and you will not notice that. You cannot return anymore, however, but you will not notice that you are passing a black hole. Even more, there is a possibility, which is a shocking possibility. If you calculate the mass of the universe, and you calculate the dimension of the universe, it turns out that we live in a big black hole. So a black hole should not be dense. It is very dense if it is small, but if it's very big, a lot of mass, it can be even very large. We may well live inside a very extremely supermassive black hole. Eh?
Is the universe expanding? Is the universe expanding?
The universe is expanding, actually. Yes, this is true. Well, it may expand because it may eat other matter from other universe, for instance. But we are now speaking of things which are not directly cannot be directly tested. So we are only saying what is possible following the physical law we know.
One last question.
Do you see the possibility of life on any other body besides Earth? You know, there's some possibility of Mars, but other than that, do you see the possibility of life on any other body in the universe?
Can you repeat the question? Are you talking about?
Is there life anywhere else?
Is there possibility of life on any other
Oh,
body?
life.
Yes.
Life. Is the possibility of life?
Life.
Is that
Where?
anybody else?
Ah, sure, that's a very interesting question. Well, we started, we, the scientific community, the astrophysicists, started looking for extrasolar planets recently, since I think something like 15 years, 20 years. This is very difficult, but it's possible today, and it's possible because we can see a star which light periodically is fainter because the planet passes in front. And we discovered already 400 extrasolar planets. So near other stars, not the sun, we have discovered here and there total 400 extrasolar planets. No one of them seems suitable for life. Too hot, too cold. But this research is so promising that I think sooner or later planets with features which are suitable for life will be discovered. This is not said that then there is life on that. First of all, there should be water. Okay, water could be there, because there is a lot of water all around. But you need also, for instance, let's consider the Earth. The Earth is not only has the right distance from the Sun. Mars or Venus will be too hot or too cold. It has also a magnetic field. It's very important, because all the radiation coming from the Sun will destroy the life, will not reform the life. It's the magnetic field which shields the Earth from the radiation of the Sun, from the charged particles. So you need a planet with the water at the right distance with a magnetic field. How rare is this planet? We actually don't know very well this. And so we don't know the answer if we are alone in the universe or if it is likely that there is life somewhere else. Let's say that the more common answer in the scientific community is that it may well be possible that there is life somewhere else in the universe, but it is likely that we never will be in contact with them because they are too far. The nearest stars are many light years from us. So even traveling at the speed of light, you may spend 1 million years before reaching another planet with life. So it's not easy to go in contact with another civilization.
Two more, and then
You had said that theoretically gravity is leaking to another dimension. If that's true, then how do we know that we're not losing gravity, or how do we measure that gravity is not reduced, or does it come back?
Well, the experiment in HC is a way. If we find some missing energy in this high energy event, and only in this high energy event, then will be a convincing that there is actually the string theory predicting the test dimension may be true. Now your question is, if in this other dimension some high energy phenomena occurs that leaks back in our universe. This is also possible. But not easy, I think, to have a sign of this. I mean, we have no sign of this. So, in respect to the question of the life, let's say that there is the possibility that life exists only in our planet. There is this possibility, because I said you should be at the right distance from a star, you must be with the water, presence of the water, you must have a magnetic field to reject dangerous radiation. There are many conditions about that. Even you must have a little bit of radiation arriving, because cosmic rays are not completely shielded by the atmosphere and the magnetic field. And the residual cosmic rays arriving, they breaks the links in the cellular matter, making faster the process of the mutation, and so the natural selection. There are a lot of conditions on the Earth which are positive. So it may be that we are alone in the universe, and this should be, for us, should excite us to invite us to preserve our planet as much as possible.
There was one more question, but I think on that conclusion, I think we're finished.